Hello, my name is Suman Saha, and I am a postdoc in the Computer Vision Lab at ETH Zurich with Professor Luc van Gool. Our paper is titled Learning to Relate Depth and Semantics for Unsupervised Domain Adaptation. Obtaining semantic annotation is expensive and labor-intensive, so we rely on synthetic to real use case for unsupervised domain adaptation, or UDA. The goal of this paper is to learn visual task relationships to improve performance on the unseen target domain. We hypothesize that an explicit formulation to relate depth and semantics help us achieve our goal. There are prior works that attempt to exploit depth to improve semantics, but they lack an explicit formulation. In this paper, we propose an explicit formulation to relate depth and semantics. We humans often relate semantics and discrete depth levels. For example, the motorbike and car are nearby. The trees and street light have a medium range depth, and the sky is far. Our key idea is to exploit this depth level information to learn more intricate relations of semantic classes. To do this, we design a framework which is presented next. Given the inputs, that is the source and target samples, our model predicts the semantics and depth maps. Then these predictions are fed into a CTRL module. However, the depth predictions are continuous valued and they don't carry any discrete depth level information. So the first question is how to extract the depth level information. We swap the continuous depth to a categorical one using the spacing increasing discretization, or SID. Given the depth range, ZMin and ZMax, and the number of depth bins k, SID computes discretization bin using equation 1. We then generate the categorical depth using equation 2. The network still learns to predict tasks independently and thus cannot fully exploit the cross-task relations. So the next question is how to enforce the network to learn cross-task relations. To achieve this, we employ a semantic refinement head, which makes the network predict semantics attenuated by the predicted depth map. Lastly, we ask ourselves how to transfer the knowledge from source to target. For this, we propose a cross-task relation layer. The entropy map generator of the CTRL takes as input the predicted semantics and the depth, and outputs an entropy map, which is then used for domain alignment. Next, look at some qualitative adaptation results on challenging synthetic to real setting. Observe the outlined areas. Our model consistently outperformed the previous state of the art for semantic class bus, bicycle, wall, motorbike, person, and the rider class. Now I will present the quantitative results. Our model outperforms the previous state of the art on 3 domain adaptation benchmarks. The major gains come from the following classes: wall, motorbike, person, bicycle, and the rider. Next, I will show some t-SNE visualization of the learned feature embedding. Our proposed CTRL helps to learn more disentangled representations than the previous state of the art, as can be seen by clear clusterization of the samples corresponding to the same semantic classes. Better clusters are annotated with circles. Finally, I conclude by highlighting the key contribution of this paper. A depth discretizing technique facilitates learning semantics at different discrete depth level. The semantic refinement head aids in learning task dependencies. A cross-task relation layer helps learning a joint space for domain alignment. For more details, please come by our poster. Thank you for your time.